So the title emerged through a dialogue, a very quick dialogue with Enzo Fano, because he invited us to say the key word of this year is interdisciplinarity. This is the key word of this series of the seminar. Can you give any talk about an interdisciplinary topic? Is okay for us to choose a topic, but the focus should be interdisciplinarity. Actually, for us, interdisciplinarity is a topic per se, in the sense that we study how people, in particular university students, deal with interdisciplinarity. So the idea was to focus about the epistemological difficulties in dealing with epistemology. So the topic is about interdisciplinarity, okay? And with the idea to focus on, the idea original was about the epistemological difficulties in dealing with interdisciplinarity, but then Enzo suggested this concept of epistemological obstacles of interdisciplinarity. Okay, we found that this was a challenge because this was not exactly a concept and a construct that we used, but it sounded to us, it made sense to us. So we accepted this challenge and we started to discuss, okay, let's talk about epistemological obstacles of interdisciplinarity, but what are them? How can we introduce them? And in particular, our point today was what kind of contribution can we offer to your PhD path from our perspective of science and mathematics education research? So this is the idea of epistemological obstacles. Just try to see if it's something that you can encounter in some moment in your path. Obstacles are epistemological in the sense that they refer to obstacles that no one can, that are the obstacles that which one neither cannot or should escape. It is not possible to escape them, or it's not reasonable to escape them, because this kind of obstacles are formative, have a formative role in the development of knowledge, both in the construction of the research in science, but also in the process of learning science. So they are obstacles that couldn't be escaped because they are structural, embedded in the process of knowledge construction. They are epistemological, but there are specific epistemological obstacles that refer to interdisciplinarity. So they are particularly obstacles that actually emerge when there are moments when in particular complex problem where there are different disciplines with their epistemologies that clash each other, and so the epistemological opposite derives and comes from this clash between different epistemologies of the different disciplines. So this is the idea. And actually, from our point of view, this is a very, very important problem, a very urgent problem as science educators, science education researchers, or mathematical education researchers, because actually interdisciplinarity is really a buzzword in some sense, but it is really an important topic in Europe and in any field, because actually we are now in a particular moment of change, of transition, of transformation, because the change in the society are so quick and so fast, and the important problems are intrinsically interdisciplinary. So the frontiers of the research, the frontiers of science concern fields like climatology, artificial intelligence, data science and computation, quantum technology, digital. They are intrinsically interdisciplinary. And we have an educational problem because typically our educational path in the school and the university are still much more based on disciplines. So we have a sort of disalignment between the kind of skills, interdisciplinary skills that are needed in order to address the frontier topics, and the kind of competence and skill that in our educational system still provide. So our problem is, how is it possible to reconceptualize, to generate the knowledge that also in our educational path how to regenerate in order to use this knowledge as a way to develop some interdisciplinary competence. What are them, okay? This was, from our perspective, just to position ourselves with respect to the topic of interdisciplinarity. So today, the goal of today is actually to give you a sort of framework, a sort of vocabulary that we use in our field in order to talk about interdisciplinarity. This is a very famous, we will present you a very, very famous approach, a framework that in our field is used, that that can help us, that we use in order to conceptualize and name and to describe what interdisciplinarity is, okay? And then we will, the second goal is actually to use this framework and an example that we will focus on in order to give you, this is our ambition, I don't know if it is possible, but to give you some tools to recognize, in case you encounter an epistemological obstacles of interdisciplinarity, in order to give you some tools to recognize it, to recognize this obstacle, and to manage this encounter with the obstacles, because it is it has some special features, and in this sense, it typically one struggles with this, but the reaction in front of this can be different. So there are people who just struggle with the obstacles. This, we will report some examples of this, struggling with the obstacles, and that's it. Wallowing in, okay, when just if the encounter typically is really can be also an important encounter, because it can be a sort of stumbling, in Italian un inciampo on these obstacles, and this can require struggling with it, but also there are people actually that navigate, diving into this interdisciplinary. It's their environment, their way to really to recognize their sense of knowledge and their way of learning and thinking. So this is another reaction, but there is also the reaction of escaping the obstacles. So we would love to give you some tools in order to recognize the encounter, see in order if your reaction is that of struggling with, wallowing in, or escaping. This is our idea. So the talk's articulation, we will first of all introduce this framework that we use. It is called the framework of Akkerman and Bakker, to name and to conceptualize interdisciplinarity. Then we will show you an application of this framework to the most paradigmatic case of interdisciplinarity, that when you ask in the school or teachers what is the most an example of interdisciplinarity, the simplest example is parabola and parabolic motion, because we are in physics and mathematics. So this is the very basic, the first moment probably in the curriculum of physics where you can discuss something about interdisciplinarity. So if you ask a teacher what is the prototype of interdisciplinarity, parabola and parabolic motion. Okay, let's go with that. Let's consider this as an example, and to use this in order to see what kind of epistemological obstacles can be encountered there, and also it is possible also to use this case to develop some interdisciplinary context. And we will apply this in order how we use with our students in our courses in order to give you some examples of what does it mean to use this topic to show what does it mean to analyze this topic from an interdisciplinary lens. And then we will present some results with university students struggling with this encountering with this epistemological, and then we will also have a presentation of a case study of a person who struggled or with a nice encountering with interdisciplinarity. As I already said, as a sort of anticipation of the story, is that the reactions of university students in physics and mathematics, also in this particular and somehow simple case, is very rich, because we can see a plurality of reactions. A plurality of reaction with also very interesting strategies of escaping the interdisciplinarity, because of course it means to go out from the comfort zone. Okay, so this is not... Okay, just before entering the Akkerman and Bakker framework, well, we are talking about interdisciplinarity. So this is, when we talk about interdisciplinarity, we are not talking about multidisciplinarity, and we are not talking about transdisciplinarity, okay? So we are discussing interdisciplinarity in the sense that when there is interdisciplinarity, it means that disciplines matter and they integrate, and there is an integration among them. When we talk about multidisciplinarity, actually disciplines matter a lot, but they're not an issue of integration among them. It's just a sort of juxtaposition of different disciplines, okay? When we talk about transdisciplinarity, typically in this moment, we discuss about the construction of a new knowledge, like, for example, artificial intelligence. Now it is really becoming transdisciplinarity because it has the contribution from many different disciplines, but it's starting to become a field that has its own dynamics that transgress the boundaries among the disciplines. So we are interested in this kind of interaction among the disciplines, where the disciplines are there and they dialogue among them and they interact and they. So the introduction of this framework, of the Akkerman Bakker framework, this is as I told, very widely used in our field, and actually it is a sort of elaboration, a construction of this idea that interdisciplinarity and interdisciplinary context can be conceptualized as a boundary zone, okay? As a boundary zone. And the idea is to use the boundary metaphor as a way to describe what happens in an interdisciplinary context. And in this framework, Akkerman and Bakker describe people who inhabit, who work in this interdisciplinary context as just one aspect. So the boundary is interesting, and also this is interesting because there is a sort of paradox of the boundary, in the sense that a boundary is like interdisciplinarity is something that at the same time connect and separate. So there is this double direction of separation and connection. Like we use this metaphor of Spaccanapoli, that is really this street that creates a separation, but this is the place where life is, and it's a melting point where there are a lot of stories. So the conceptualization of interdisciplinary space where there is this double movement, interaction and separation. And to inhabit this boundary zone means also to play a role as a researcher, as people of boundary people. That means to be at the same time in a field that you feel a sense of belonging, but also a sense of not belonging in this field. But one interesting concept is the concept of boundary object. This is something I would love to a little bit articulate, and inviting you to think in your work, if you deal with some concept or object that can be boundary. Boundary object is rather complicated, mainly for physicists and mathematicians, because the boundary object is something that has intrinsically a sort of ambiguity, okay? And typically, both physicists and mathematicians tend to define the object, and also philosophers, I would say. So, just to close the object within a definition, and to give the process of definition of disciplinarization of this object, and to close the meaning of the in a boundary zone, a boundary object has a sort of ambiguity because there are different possibility of interpreting. There is an interpretative flexibility that is not easy to be managed. Also because this object has the feature that can be an object that belongs to both one word, a discipline, and another word, but at the same time neither, it belongs neither to a word nor the other. So it has this double nature, both and, neither nor. Sorry.
Just to clarify, black holes, would be a boundary objects or not?
A black hole.
Because it's also an object
yes.
of every day, in a sense, because black hole.
This you mean every day in the sense that you mean you use the metaphorical meaning.
Yeah, obviously.
So this is it depends on how you use it. We are not talking about the metaphor of the object, but for example, the concept of we will for example the concept of time. Okay, the concept of time or the concept of space we are doing with Enso's concept. Space and time, for example, are two concepts that are foundational for all of our disciplines. The concept of space is foundational to establish mathematics as a discipline, is foundational for physics, is foundational for philosophy, but so it not only belongs, but it is at the very basis of our concept of disciplinarization of the knowledge. But so they are part of the disciplinary identity of our disciplines, but at the same time, they belong to all the others. And there is this movement of disciplinarization and also to go out and to, in the history, I mean, space and time, it's an object that that passes from one discipline to another. We will discuss later, it was, for example, in the concept, in the module of parabola and parabolic motion. What can be objects that are boundary objects because they typically are foundational to the description of the motion in physics, and also they describe parabola in mathematics. We discussed a lot about this. So we were discussing in an interdisciplinary a boundary object, something that can belong, for example, paradox. A paradox is something that is philosophical, physical, mathematical, okay? And they are different objects in the sense that can play different roles with different aims, different rules, different way to manipulate and to analyze them. I remember that your thesis was about the black hole because, okay? And one aspect that they describe very in detail is that let's imagine to be in this boundary zone as boundary people using this boundary object. I need to take the, and this is the main idea. In a boundary zone, like in an interdisciplinary area, the mechanism of learning and addressing a problem in this context is special, is different, dealing with learning in an interdisciplinary context with respect to learning in a disciplinary, monodisciplinary context, because they analyze many different papers and works to see if it was possible to recognize different boundary learning mechanism at the boundary. And then they identify these 4 mechanisms. The first one was identification. Identification means, for example, to deal with the concept of paradox among a physicist and philosopher and mathematician. The first part is just to try to recognize that how I talk about paradox is different from the work a philosopher used to talk about the paradox and the mathematician talks about the paradox. This is called identification. So like in a boundary zone, when you recognize some specificity of your way of reasoning, just because you are encountering someone else that uses the same word in a different way. So at the boundary, you have some awareness and some feedback about your specificity. This is identification, when the boundaries becomes much more clear, they become clearer just because the encountering with the others feedback with some specificity that you didn't recognize if you are just in a discipline. Another mechanism is the coordination. Coordination means that when you are in this boundary zone, this was something that we discussed always, you need to try a way to communicate. You need to try a way to clarify, to make your assumption explicit, to find a way to the word to cross the boundaries. This is the coordination. The coordination, you see, the identity of the different identity becomes clearer, but they remain the same. Instead, in the reflection is another mechanism. This is the most complicated one. Here, it typically where also the epistemological obstacles come out, because reflection means that you are there in a process of trying to make at the same time a perspective making, a perspective taking. You are trying to analyze the process also from the other perspective, just to change your position with respect to the problem from one side to the other. So perspective making and perspective taking. And this is a process that typically also feedback about your identity and the impact about enrich your way of reasoning to the same object. The last one is transformation. That is instead when actually in some moment the habits and the way to work together create a common language, a common way of addressing the problem, and there is a new knowledge that is built just because of this way of dealing with a project with a problem in an interdisciplinary. Do you have this picture? Just it would be nice for us to understand about your a little bit about examples of your PhD work, and to try to understand what kind of many of you, I guess, are working in some interdisciplinary field, and what kind of interdisciplinarity are you encountering? Are you in an interdisciplinary problem? Context? Are you dealing with some interdisciplinarity is something that is part of your experience as PhD students? If so, what disciplines are intertwining? No one? All?
Yes. I maybe.
Ah,
can you hear me?
Yes.
Yeah. Hi, I'm Francesca. My PhD research project is about time. So it's in interdisciplinarity, as we said before. I study the concept starting from Aristotle and comparing the relational characteristic of time, arriving to Einstein and relativity. So I'm at the beginning, I'm a first year, so this
so
is...
the disciplines that are involved in your are, so philosophy?
Ancient philosophy and physics.
Philosophy and physics.
Mathematics,
and
geometry.
Some epistemological obstacles that you could have the feeling that is just because of this interdisciplinarity of the...
Yeah, because each discipline, each level, every discipline has a different level to understand and speak about time, maybe.
Sorry?
Maybe philosophy and physics, every discipline has a different level of definition of time. Maybe I'm thinking to there is Carlo Rovelli. He said that we can speak about a different level of time and different level of where we are understanding its war. The definition can differ from maybe if we speak about our brain, if we speak about the micro level of reality, or if we go to the macro in the cosmology. So it depends on the level that we look at the reality and the level that time work, if we can say work in that level. I don't know if I
very interesting. We will let, yeah.
Okay.
Thank you. Someone?
Quando poi io posso parlare un po' in italiano, un po' in inglese, tutto vale.
Okay. But your PhD is about?
All the pantographica, speech meter, unification.
Okay.
Sobre proceso ecosistemico.
And do you encounter some, and I mean, and in your research group or your path are you encountering different disciplines or different people working in different disciplines?
Bueno, specifically in my research, no.
Okay.
But like a biologist, I think that in the recognized different species where the definition could be a definition genetics, morfológico,
Okay. Yes.
coevolutivo. Entonces, per definire una especie entran paradigmas de genético, coevolutivo, morfológico y se torna molto difficoltoso definire lo che è una specie.
Ok, wonderful. Thank you.
Potrebbe essere un
certo.
boundary limit.
Yes, thank you. Others? Is there someone else who want to? Okay. So let's see how we struggled with this, how we use this framework in this historical case of parabola and parabolic motion that actually is in our disciplines are very basic topic that are taught at the very and actually in the history, even if it is natural to think that there is an interdisciplinarity between parabola and parabolic motion, actually in the schools there are the different narratives that have been consolidated, and typically they are addressed in rather different way. There are rather typical narratives. So if we think about a parabola in mathematics and in a mathematical textbook, you cannot avoid to think of defining parabola through the quadratic equation. You need to have the Cartesian frame of reference, and this is the definition of parabola. Does it make sense to you? So the mathematical object, parabola as a mathematical object, is typically its equation. Okay? If we think about a parabolic motion, actually, typically, this is an exercise that is done in order to apply the composition of the two motion, the uniform accelerated motion on the vertical and uniform motion on the horizontal. And so this is a falling body, and you can demonstrate actually this is a parabolic motion, because to combine the different motion, you have an equation that can be recognized as the equation of a parabola. So this is typically the way in which parabola and parabolic motion are presented in our textbook. Actually, this is an example of how in the historical evolution, in the disciplinarization of the evolution, actually we don't see in this story how in studying the history and in the co-evolution of mathematics and physics, this topic was so important. And in order to arrive at this description, these narratives, actually the disciplines had to encounter and to struggle with many epistemological obstacles of interdisciplinarity. This is an episode in the history of physics and mathematics that is very, very, very deeply addressed, because it is foundational for physics as a discipline, and also it represented a moment, very important moment in the history of mathematics. And this in this co-evolution, struggling with the interdisciplinarity and epistemological obstacle disappeared in our narratives. So we tried to regenerate and to reconstruct the historical evolution of this in order to unpack example of epistemological obstacles, and also we use this in our context of pre-service teacher education in order to guide them to develop this kind of competence. And also to avoid, actually, this is very important. When we think about interdisciplinarity in mathematics and physics, typically, there is a sort of instrumental approach. I, as a physicist, use mathematics as a tool because it is useful to quantify or to formalize a problem, not because of its epistemological features, not because of their epistemic practices of reasoning. I just use it as a tool. At the same time, mathematicians use physics as a useful context of application, not just to use that mathematics is useful for something. It's not just something that lives in this way. So this is the path that we develop. I don't want to enter it. Just I want to give you the kind of discussion that we had. We decided to create this path and this reconstruct this interdisciplinary analysis based on two boundary objects. We decided, I mean, there are many boundary objects. We took curve and proof. Curve, what is a curve in mathematics? What is a curve in physics? What is a curve in your disciplines? And proof. These are words that we use, but we discovered very soon that we conceptualize them in very, very, very different ways. For example, on the idea to use the curve and proof as boundary object, we started to go back in the history of physics, history of mathematics, to take some images and that could recognize some curves that could be part of this story. And okay, these are curves. What do mathematicians see in this? What do these big images represent? Are they representation of a parabola, of a parabolic motion, of something else? What kind of, how do we read this kind of course? What kind of interpretation can we give? Sorry? Motion of object, which one? All of them? Also this one? Ooh. This one? And the last one? This is the linear motion. This is an inclined plane. Yeah. What is this? Do you recognize this picture? This one? Mixed motion. You are a philosopher. Mixed motions. This is from Tartaglia. You see how many things you can. Is this a parabola? What about this? Does someone recognize this one? This picture. This is an historical picture. What solution? This is Galileo's proof. This is the proof that the motion, the trajectory was parabolic. This one, you have absolutely to recognize. You are here, you have to recognize this. This is part of this. Guido Baldo del Monte. Great. This is PSSC. This is it. And what about this? Is this a parabola? Why? Is for the other, is this a parabola? And for what kind of curve is this one? Can we tell it? What kind of curve is? Why do you say that? How can you infer this? What are the elements here that you can recognize? You read too much Guidobaldo del Monte. Actually, it can be it can be a catenaria, a parabola, an hyperbola. It depends on, I mean, you need to define it, you need to put this object within a system and a theory in order to decide what this object is. But typically, this is this gestalting picture of parabola. If you think in your mind what is a parabola, this is typical, a kind of picture like this. So we started to use this one, and we started to ask, for example, ourselves, okay, what a physicist see in this picture? What about a mathematician? For example, how in order to make this identification, to recognize the different possible readings from the different perspective. And then we worked on these images and this concept in order to try to understand what kind of communication we could activate in order to understand better each other. And then that was, of course, a sort of result of our work, but it was the most important part, that in front of, for example, this Guidobaldo del Monte picture, it was a nice exercise for me, for example, to think, okay, now here, Laura, what could she see here? What can she see? What a mathematician can recognize here, and vice versa, to make this perspective thinking and perspective taking. And then, of course, these are questions that okay. So let's enter much more specificity into the epistemological obstacles. Actually, as we decided that in our epistemological analysis, there were 3 moments that were fundamental in this story. One is the first one, so I can already unveil the Tartaglia picture, the Guidobaldo picture, and Galileo picture, because they are 3 important moments that, and to move from one moment to another, it meant also to address epistemological obstacles due to this. This was our goal, where mathematics and physics encountered. So let's see about Tartaglia. What kind of epistemological obstacles can we see? So Tartaglia actually had a practical problem. His was the practical problem to find out the angles of the canon in order to have the maximum range. That was a practical problem. And this was very important because it was a practical problem that pushed him to take a physical, what mean in that period, a problem of understanding the heavy body, okay, the motion of heavy body, take this problem from the debate that was physical, that was a discussion about the causes of the motion. What are the reasons of the motion? Is it violent? It is natural? So the causes of the motion. And he took this problem, and instead he put this problem in a boundary zone that was practical. And in this practical, to move this, he changed the questions. The question was not what is the origin of the motion, of the causes of the motion, but what is the shape of the trajectory. The shape of the trajectory was not an allowed question in the debate in the motion of the falling body. So he changed the question, and he started to ask a question that became a boundary question, an interdisciplinary question, because the shape of the motion required to use the mathematics and also the philosophical, metaphysical knowledge that was at the moment at disposal, okay, that was available. So he changed the problem, And in order to deal with the problem, we had this obstacle. How can I describe, draw the shapes of the motion, of the trajectory? And he made this trajectory. What is there behind this trajectory? What kind of knowledge is here represented to address this problem? The question was new, but the problem of how to address the knowledge, he had to intersect knowledge from different fields, because what is represented here? Mixed motion. What does it mean, mixed motion? What does it mean? What is this? Why? How can we describe this trajectory? It's a combination. It's the first part, and it's a violent motion, and it is represented through what is the mathematical object, a straight line. Okay, so there is a straight line, that mathematical representation to represent a violent motion. Here, a straight line, and the motion, what kind of motion was this one? Free falling, and in the medieval language was the natural motion, because the heavy body had to reach the natural locus in the. So we have a violent motion, a natural motion. That was a little bit complicated. Indeed, that was the problem, that he discovered that it was not exactly but there was the mathematics that was possible, that was just an arc of circumference. So here there is a mix of metaphysical, philosophical, Aristotelian, I would say, knowledge and the interpretation of the emotions in terms of natural and violent, and a way to recognize the mathematical aspect of this. So here, in this moment, the parabola was not conceived as a possible way to represent emotion. It was not part of the interpretative scheme. Also because actually the book of Apollonio, the Conics, was just translated in the same year of the book of Tartaglia. So this was important in order to enlarge the mathematical concept and to enlarge the discussion in this interdisciplinary boundary, in order to have a new also mathematical knowledge. In that moment, Tartaglia didn't have this. But actually there were a lot of other epistemological obstacles that needed to be addressed, because behind Tartaglia there is not a limitation of the mathematical tools, in some sense, of the mathematical knowledge in this sense, but also because there was a projection of a cosmological, I will say, view of the world, where there was not only in a cosmological world, where it was in the celestial world, there was just the idea that the only possible line to describe, to use as a mathematical tool, were the circumference and spheres and the straight line. There is this distinction between the perfect way and the material way in the sublunar way, and there is this distinction between basic motion in terms violent and natural movement. So there were so many epistemological aspects, in the sense that it was important to break down the value of perfection. And also to consider acceptable also shapes like parabola or the other conics, for example, and also to break down the material distinction between the perfect world in the celestial sphere, and instead a corruptible matter in the sublunar world. And also and in this sense was important, because it was important to accept the idea that it was possible to mathematize and to use mathematics as a form of reasoning, as a form of establishing the truth of a reasoning. and to move from a sort of metaphysical reasons to accept mathematics as a way to accept the validity of a statement in the sublunar world, and also the classification. So actually, while in the same time that Tartaglia was trying to use this problem of addressing the ballistic use in the sky, of course, there was also a process that enlarged the concept of perfection, and it was possible to include also the other shapes, the other conics, in the description of the world. Of course, Galileo break down the distinction between the matter in the celestial sphere and in the corruptible matter of the sublunar world. But then we arrive to Guidobaldo. Guidobaldo, actually, when he made this move, he decided to make something very important in the history of our disciplines, and to change the relationship between mathematics and physics, because he somehow, in this dialogue with Galileo, he invented the concept of experiment and the idea that it was possible to use data and a lab and the collection of information through an experiment in order to redefine the concept of curve. Okay, so Guidobaldo made this experiment. He took a ball just with some inks, and he, in order to address it, to search for the trajectory, the shape of the trajectory, he made this experiment. He took this inclined plane, and then he threw the ink dirty ball, and he collected this information. He collected data, okay, about the world. So this is a curve that for physicists is very typical. For a mathematician, this is just a collection of dots, okay? So this is a curve that is created by the representation by collecting data. And here it was very interesting, because Guidobaldo, in his notes, he described very clearly this procedure that from the experience is turned into an experiment, acceleration into interpretation, the invention of the experiment, okay? And but the question remains, what curve is this? What curve is this? It is similar to a parabola, he said. It is similar to an hyperbola. But how can we decide the curve? What reasons do we have in order to decide what is represented here? This was an obstacle, in the sense that he had to invent some reasons and some way, a way to make a statement and to validate this and to decide what kind of curve was this. And he didn't use a mathematical reasoning. He didn't complete the mathematization of the process. He just made another kind of reasoning. He said, you are in the material world. We are not in the mathematical world. We are in a material world. So we can have good reasons to say that this curve is exactly the same curve that has a chain, a material object. We are in the material world with a material object. This is the same shape that has a chain just up. So the idea is that it's a catenary, just because it's a material, the shape of a material object. That can be also interpreted in terms of the shape that can be obtained by combining violent and natural world. This is also still part of I don't want to enter in this one, but he didn't have he didn't produce a mathematical proof. We needed to arrive to Galileo to do this. But here we needed to accept, to go out and to deal with a new epistemological obstacles that was how to conceptualize and to accept that mathematics as a form of reasoning, as a way of proving something and to establish the validity of an hypothesis become part of the science in the sublunar world. But this is now I pass. Now I can now because we are entering in the mathematics world. I leave the floor to Laura. But first of all, I would love to. I don't know if maybe we can finish this one, or do we want to some comment questions until now? Until now.
Was very nice the way Akkerman was before, but you feel that having the traditional way, you're modeling from different ways, the reason 500 years later is identical. So we managed to simulate from one side with the analytical, we managed to do on the other side with polynomial mode. What else can the merger of the two black holes? We don't know. And so we connect. We don't know what's there.
This is the kind of, because in this, if you go to the history to this you recognize, you recognize where the limit of your models, and because and this is really the moment where the new knowledge emerge, because you need to reframe the problem in a new context in order to or to invent a new mathematics, or to reframe the problem and to I think that Tartaglia was amazing in this case, because it's in the history of physics is very nice to take the problem, to change a practical problem, and to put the problem in another position in order to change the question. This is reframing the question. So and the question of what is the shape of the trajectory was so productive, because it opened. Of course, it was a question that didn't have yet the tool, but it was an interdisciplinary reasoning that could help to find and this is, yeah.
So before proving the fact that the trajectory of the motion of a projectile is a parabola, do you all believe this is true? Is it the same to say parabolic motion and the motion of the projectile in your mind, in your experience? Have you ever doubted? Do you have any doubt? Have you ever thought that the motion of a projectile could be something different from a parabola before? Very.
Kind of basic, yeah.
Okay, so the first thing we have to consider when we reflect on proof, because in Galileo we move to proof, so it's something very, very important as a shift from the epistemological point of view. Before it was kind of trying to interpret the motion using the Aristotelian point of view. Then trying to see what kind of curve it could be, but proving is something very, very demanding. Okay, and so before proving that the motion of a projectile is a parabola, I want to show you something. Okay, so what is the motion in this case? Do you see a parabola here? Let's try to describe this motion. This is a projectile motion. Is this parabolic? What do you see with your eyes? I do it again. Okay. So the phenomenology of this motion in reality is much more similar to Tartaglia's interpretation than to a parabola. I think you agree. So it seems that the first part is right, and then something, I don't know, and then falling down. Okay. So this is very, very important if we want to think about the struggle with the epistemological obstacle, because for a mathematician, we prove something to say something is true within a theory. So proof is related to truth. Okay. But when we prove inside a science, for instance, we use mathematics to prove, not just to show, to try to approximate the trajectory, but to prove that the trajectory is a mathematical curve. Somehow we enter a world that is no more mathematics, but is something that's more related to philosophy. What is true? Is it more true that the trajectory is a parabola, or more true that the trajectory is the one Tartaglia was trying to show, or more true that it is a catenary? So it seems that we are dealing with something very, very critical. But in general, in the culture, I would say, of most students, people, and so on, it is the same. So parabolic motion and motion of projectile are the same. This mirrors a specific relationship between mathematics and physics that is typical of our current understanding of the role of mathematics in physics, but very often this is completely implicit. So nobody complains about elementary physics. Maybe we start reflecting about this relationship between mathematics and physics with quantum physics, or maybe contexts where the phenomenon is not so easy to detect, or the models are very, very complex. But it is something that from the very beginning we have to deal with. So Galileo's proof. The first important thing is that we are not talking about a proof kind of over-interpreting Galileo's intention, because indeed in the book Methods and Demonstrations, can I translate it this way? The title, okay, Discursive and Mathematical Demonstration related to two new sciences. This statement is really presented as a theorem, and a projectile which is carried by a uniform horizontal motion compounded with a naturally accelerated vertical motion describes the part which is a semi-parabola. So it is presented as a theorem and proved as a mathematical theorem. This is a diagram that is not a Cartesian diagram, so nothing related to what we see in textbooks. So no y-axis, no graph of a function, nothing. Okay, this is a very, very interesting diagram, because it's a tool to prove that these points must belong to a parabola. That uses at the same time an interpretation of time, a spatial interpretation of time. So time is represented with a segment in the space, and geometrical segment. Nothing like this has been done before. So no time before, and no spatialization of time. And this diagram also allows to combine what we today name the equation of the motion in time, so the equation of evolution in time, la legge oraria in Italian, and the trajectory of the motion that is in the space. So usually we describe the motion with two graphs. One is the graph of a function relating space and time. The other is a graph of a function of the representing the trajectory in the Cartesian plan. This diagram embeds both, and the trick is that since this motion is uniform, you can represent with the same segment the time and space somehow. So before reading the proof of a theorem, I introduce what we can consider a theorem from a mathematical point of view. When we have a theorem, we have a statement, a proof, and a framework, a theory that allows us to say that the theorem is proved. A theorem is a statement proved inside a theory. So this is nothing related to truth in general, absolute truth. Every theorem depends on the theory that is behind the proof. Okay, so if you want to prove something in the Euclidean geometry, even if you don't mention that you can build the perpendicular line, there is only one parallel line for an external point and so on, you live within inside the theory. And so all the statements are true in a specific context and following kind of meta-theoretical rules also. So we use modus ponens, we use different structures of deduction, and the truth of the statement depends only on this kind of meta-theory. So looking at Galileo's proof, we can see that before the theorem, there is a long introduction where the first thing that is introduced is, of course, the uniform motion. It's not in the fourth day, but in the third. And it's introduced this idea of uniform motion without talking about velocity, for instance, or speed. Today we say uniform motion is a motion when you have the velocity. I don't know if velocity or speed, maybe both, are constant. Okay, but you don't need to use velocity to say what is a uniform motion. And what Galileo did was extremely accurate, because he used for the whole proof and in all the book only ratios of commensurable magnitudes, and used all the theorems, the Euclidean theorems, related to ratios of commensurable or uncommensurable, but homogeneous magnitudes. So it defined the motion also using this mathematical tool. The tool he could manage from the theoretical point of view inside the Euclidean theory. And also he decided to define what was a projectile. Now in the textbook there are usually examples. Some people make mistake interpreting projectile. The projectile refer to a gun, so in the common language, but projectile is defined using the idea itself to combine a uniform horizontal motion and an accelerated vertical motion. So the definition itself of projectile is a body or an entity moving with this kind of motion. Before, Olivia mentioned this picture from the translation of the Apollonius work on conic sections. Also Federico Commandino translated Apollonio, so another very important scientist from this city, I think. Why was it so important? Because before we said what is a parabola, and Olivia mentioned the equation of the parabola. So you studied parabola mainly as a function with an equation in the Cartesian plane. So if you think about the period, so the analytical geometry had not been developed, or Descartes had started working on it, but even Descartes didn't use the Cartesian plan because he was just connecting geometrical constructions, and algebraic expressions, not functions in the understanding we use function today. And it was very important for Galileo to rely on Apollonia because you can characterize a parabola as a section of a cone using only ratios of homogeneous magnitudes. So you can say that it is possible to identify a constant, a fixed length, lato retto, and that is using a proportion, and there is a quadratic proportion between the, maybe I can do this laser. Okay, do you see the red point? Okay, so here you have a segment, and here you have another segment. Can you see here a kind of Cartesian plan? Where this is the y-axis, this is the other axis. Okay, so if this point is on a parabola, do you agree that this is what we name the abscissa of the point, and this is what we name the ordinate of the point? Can you see something there? Okay, you don't need the Cartesian plan to prove within the Euclidean geometry that there is a fixed quadratic proportion between the length of this segment and of this segment. So what we express as y equals a multiplied by x squared can be proved completely in a geometrical way using only ratios of homogeneous magnitudes. So Galileo could start, now I don't think we have time to read all the proof in details, but just to give you an idea, Galileo had derived the quadratic proportion with time with other experiments. So we have here an accelerated motion, so he could use the quadratic relationship with time. At the same time, we have a quadratic relationship with space. So he proved that these points that are the points that the body cross falling must be on a parabola. Okay, so the proof is a completely Euclidean proof, but as Archimedes had already done in the past, some of the theorems were not geometrical theorems, but were theorems coming from kind of experimental setting. Okay. So now you can be convinced, since you trust me, I am a mathematician, so you would never complain, that we proved that the trajectory is a semi-parabola, so an arc of a parabola. So now I want to reflect with you about something. What kind of relationship you can see between mathematics and physics in these three paradigms? But in particular, in the last one, how do we deal with the issue of truth? So is it more true that the trajectory is this one? Is it more true that the trajectory is this one, since it comes from data collected? Or this one? In your mind, in your feeling, what do you consider more true? This or this? The last one. Do you all agree? Do you all agree? So, and why? I want to force you to meet an epistemological obstacle, even if you didn't want. Okay. So you feel the last one is more correct. Okay. I think that if we show you a textbook with the questions, you feel it's even more correct. But this is the most correct of this slide. Maybe. Other feelings? Except nobody is complaining. Okay. So in this case, we are accepting that what we prove with mathematics brings more truth than what we observe, and we can infer from the background, the metaphysical background, and also from observation. An important aspect to consider here is that this is true in a mathematical sense. So it depends on assumptions at all theorems. I said before that we have a statement. In this case, the trajectory is half of a parabola. And we have a proof, geometrical proof, adapted with some empirical theorems, and a theory. Okay, here we have a specific assumption, that is that these lines represent the gravitational field. Okay? These are parallel lines. Is this okay for you to represent this way? Okay? What if I take the Newton law of gravitation? Is the field made of parallel lines, the gravitational field? It's not. Oops. Okay, and we would say, well, now we have these mathematicians are really too focused on details. But if you take parallel lines, you prove it's an arc of parabola. But if you take the other model, you prove it is an arc of ellipse. Okay? So it's really something true in the mathematical sense. So not an absolute truth. But if you take this, I don't want to say too much, I am afraid to make mistakes here, but I think this is an image, maybe a diagram inside the physics, representing an experimental thought experiment by Newton. So if you start, maybe not with the paper sheet, but something a bit more suitable, if you start launching it with the more far and with the and higher velocity, you could observe that the body does not fall onto the Earth. Here you see there is an assumption that the Earth is flat. This is very contemporary for many Americans in particular. But if you more decide that the Earth is a sphere, there are assumptions here in this model. And you can imagine to launch it so far that it can fall onto the Earth. And you can imagine this kind of behavior. Okay, this is not something so unreasonable. We know that indeed this can happen. So changing the model changes also the shape of the curve. And we are not changing mathematics. Here we are changing the physical assumption of the model. Okay. Of course, we can show that it's since a parabola is a limit curve, so we can just have one parabola. We can have infinite ellipses, infinite hyperbola, one parabola. Okay, so it's very difficult to prove that something is a parabola. With data, you cannot do it. You could never do, as many teachers propose to do, you take GeoGebra and you put this drawing in GeoGebra and you choose one equation of a parabola and you start changing the parameters. You can fit very well this data with the parabola. Okay, you can fit very well this data with an ellipsis. You can fit very well this data with an hyperbola. I guarantee that this is possible, because the issue of proof is not fitting the data. Okay, and since parabola is only one, imagine to cut the cone with the plan. You have only one position is parabola. Before and after is ellipsis and hyperbola. So you could never take care of the error in a sufficient way to prove that something is a parabola starting from data. You can just prove it starting from the model. Okay. So this is very, very interesting, very, very complex. What's time? I don't want to steal time to Francesca, our testifier of the navigating the interdisciplinary. Okay. We said before that these obstacles come from the evolution itself of disciplines. When we are taught mathematics and physics, the idea is you build mathematics, you build physics, and you can apply mathematics and physics. So you have the toolbox. I die every time I hear the toolbox to apply to a physical problem, or physics as a context where mathematics is too abstract and senseless, can have some sense somewhere. Okay, so this is the big picture where we are educated. So separated disciplines and some interactions here and there. And if you look at the history, we see that there is an evolution that sometimes is very, very demanding. And the case of Galileo is, I think, paradigmatic. So the debates about the view that Galileo brought into the natural sciences is one of the most famous debates in the history of, I think, of culture, not only history of science. So when there is an epistemological obstacle, you have to discuss a lot. You are never convinced. You must be moved from the discussion about truth, for instance. And to what extent can mathematics bring some truth inside the investigation of nature? This is not so obvious as you learned to believe. Okay. In our approach, we decided to bet on a virtuous circle between interdisciplinarity and disciplinary authenticity, using interdisciplinarity to discover the epistemological roots of our disciplines. And since the evolution is a co-evolution, we cannot discover the roots of our discipline without considering the co-evolution and interaction with other disciplines. It's the same in this place of the projective geometry. I am in love with projective geometry that could never be developed without the art and prospective optical studies and so on. So the roots of the disciplines are, in particular, when big changes, big choices are made, are very, very often related to interactions with other disciplines or reframing of problems with a different framework. Okay, we decided to invest on this evolutionary view of epistemology and the interdisciplinary authentic view, and not just something reconstructed as an artificial connection between things that can be easily separated. And we proposed these to prospective teachers, and we present two cases. We don't have a lot of time, but in the first case, we will present the results of a paper with this framework, the critical encounters with the interdisciplinarity. What does it mean to not only encounter, but encountering these obstacles with a critical attitude and really struggling in a positive sense with these obstacles and not just skipping them or escaping them. Then at the end, we will reflect on another case study that is not related to the implementation itself. So not what the first studies is about what happened in the discussion between our prospective teachers with the mathematics and physics background, discussing about this proof and about the way it was presented in a textbook today, the Walker textbook. While in the second case, we will reflect more on the, let's say, the global effect of this experience for prospective teachers at the end of the implementation, when they had to kind of sum up what they learned for themselves from this case, and how, and if, and how, whether and how, we were able to trigger kind of reflection that changed their own view of the discipline, their own discipline, the view of the other discipline, and of the interaction between the disciplines. Okay, in this first set of data, I will present you 3 cases, and I suppose you are not used to the methodology of research we use, that is a qualitative, not only qualitative, there is also quantitative. There are quantitative methodologies in mathematics and science education, but where we learn more is with the qualitative analysis of reasoning, because we are not interested in how many students really at the end are able to reproduce exactly Galileo's proof. This is not really relevant for us. But what kind of different attitudes, behaviors we could detect in this interesting set of people, because it was master students, mathematics and physics, prospective teachers, so interested to become teachers, and meeting maybe for the first time a challenging issue that obliged them to rethink about the epistemology of the discipline they are educated to. We discovered that also students in the Master of Mathematics never reflected about what is a proof, not from the epistemological point of view. So they learned hundreds of proofs without wondering what is proof. Okay, and for physicists, it was a bit better. We realized that physicists were more critical about the possibility to accept a mathematical proof into physics than mathematicians. Okay, and we discovered a lot also about their view of proof. So taking proof and putting the proof in the boundary between mathematics and physics with an educational perspective, we discovered a lot about the view of these master students and prospective teachers about proof in physics and mathematics, and also we discovered how they decided to encounter these epistemological obstacles. We referred to a framework developed by 2 researchers in math education. The first is very, very famous. Louis Radford developed a whole paradigm of research in math education in the sociocultural paradigm, but I don't want to explain this here. It would be a nightmare. So just to explain you very, very briefly what it is, the idea is that investigating mathematical thinking from an historical point of view, we discovered that there are many dimensions we have to consider. So the thinking, reflecting also historical issues, social issues, and that can influence the scientists. For instance, Tartaglia would have never maybe explored the shape of the trajectory without being interested in ballistics and without being in the context where he lived. But an important aspect stressed by Radford is that this is not a matter of psychological or subjective relation, direct relation of the subject with the problem, but there is a very, very important mediation of the culture. So we meet something with a cultural eyes. You did the same. You did something similar before. You are educated to see parabolic motion in a specific way, and you are educated to assign to mathematics a role in physics. You didn't complain. When you look at the evolution of the relationship between mathematics and physics, the different way to incorporate mathematics as a reasoning and not only tools in physics, you start reflecting and saying, okay, maybe it is, I have to reconsider what I have been taught, not just to become skeptical about everything, but to become aware of the choices and to understand deeply that there is an evolution, that we can position, reposition, co-position in different ways with respect to knowledge, not only the results, the product, but the method itself and the source of truth of a method. This is very, very important today in particular. People do not believe in science anymore. So we have a problem with the epistemology of science and the relationship between science and truth. If you say there are equations, there are scenarios, please you take in consideration, or there is the climate change, please take care of your choices. Also from the political point of view, we know that in 30 years, something can happen very bad for you. And they say, okay, but they said climate change, global warming today is very cold today, and it's April. Okay, so you see that there is a different relationship with truth. If I have cold and it's April, I cannot believe that there is global warming. What is this global warming? Look at these equations. There will be global warming, there is global warming, and there will be a disaster in the future. So we ask people to trust science at a certain point, but if we don't really have a critical encounter with science, it's very difficult to develop a personal point of view on this and trusting science also. Okay, so we decided to address two research questions, one more theoretical, the other more empirical. And I will show you some examples of the second part, the empirical part, about critical and acritical encounters with the proof, Galileo's proof compared to the textbook, the Walker proof, in a group of students. It's very, very important to consider that very often the implicit epistemology of interdisciplinarity between, we have to close. Here's some, okay. It's okay, so I can just skip all this data, but show you the main behaviors we observed in this case. The first, I bit of ironically describe the behavior as a critical encounter, so encountering epistemological obstacle without realizing it. Okay, so you can be in front of an epistemological obstacle, but being so educated to think about science in a specific way that you don't realize it. And it's the case of a student that considered the proof presented today with algebraic language more rigorous than Galileo's proof, because Galileo had no tools to be rigorous. We have tools to be rigorous, use equations. So, okay, it's kind of fairy tale of the past, but the truth is what is in the textbook today with equations. The second case is interesting because the students really stumbled and struggled a lot with an epistemological obstacle, but At the end, they separated the process of presenting the proof with the proper proof. Decided to interpret all the construction of Galileo as a just kind of communicational issue. So you have to explain all the steps, while in the other cases, you don't need to show all this stuff. There is a proper proof that is quickly performable with equations. So they recognize the difference, but they decided to escape this complexity. And in the third case, again, the students encounter and struggle with this epistemological obstacle, but they found a way to separate completely, again, the notion of proof in mathematics and the notion of proof in physics. So when they were exposed to the interdisciplinarity, they decided to say, okay, our colleagues, mathematicians, said that it's enough to have hypotheses and thesis and something in between. So this is a mathematical proof. The physical proof needs explanation. We can separate. So they reposition proof in mathematics and proof in physics as different objects, taking the proof out from the boundary zone and redisciplinarizing very, very clearly proof in math and proof in physics, and avoiding the epistemological obstacle. So we observe that this attitude to escape the epistemological obstacle is the most frequent in prospective teachers. Sorry if I took so much time. In the last part, last 5 minutes, I will give the floor to Francesca to present her experience as a student of our courses.
One of the modality to inhabit interdisciplinarity is characterized with a dive into this boundary zone. And it's the third method to inhabit interdisciplinarity. So I wonder why I like interdisciplinarity. I like to be into the boundary zone. And Professor Levrini and Professor Branchetti asked me to present a brief personal trajectory that is characterized for the first time in my bachelor thesis at the University of Pisa, was developed in a magnetic resonance laboratory. And I started to be in a boundary zone, inhabit with the psychologists, image analysis, and as a physicist, I starting to collaborate with different disciplines. And then I felt that my discipline was totally not enough for me. And I searched for something that could bring me in a more big horizon. And the answer was the Master in Science Communication at in Trieste at CISA. And there were a big experimentation with interdisciplinarity many years ago. And the classes was conducting and designed with different disciplines. So we were physicists, biologists, mathematicians, and humanities. And we started to collaborate to communicate science. So communication was a key, but not only because communication is a language. Communication is also a discipline, and the importance of interdisciplinarity is to acting this kind of mechanism Professor Levrini speaks about before. The Identities project, I participated as a pre-service teacher to the Identities project, and there I started to rethink mathematics not only as a language that can describe reality, but also as a producer of knowledge itself. And because maths is a strong argumentative structure for reality, and you can consider this not only for describe and and communicate science. Now, to describe what I thought to do with this kind of skills, I'm working on this kind of constructed epistemic emotions, and that you can consider this as a boundary object, because epistemic emotions are those emotions that intervene in cognitive processes, and you can study that. You can study them with the key of psychologists, with the key of knowledge, and in particular, I started to study them in the context of special relativity. So using a text, an historical interview conducted by a psychologist with Albert Einstein. So there are also in the boundary zone, in the interdisciplinarity zone, there are obstacles within the zone. So there is not only obstacle to get inside interdisciplinarity, but also if you inhabit in the boundary zone, you can find something that is very difficult to manage. For example, I want to share with you this kind of obstacle, institutional resistance, because, for example, psychologists of physics, it's a very strange thing to do research within, and there are, for example, there is an article by Miller that told about a controversial action between psychologists and the historical of physics. And then there is one of the classical epistemological tension, because if you want to describe emotions in a psychological way, you can manage the complexity, because you can describe emotion in a very particular way using the language. But if you want to describe them in a quantitative way, you have to be very, very synthetic, and you can just oppose. You have to interact. You can make it to interact disciplines that are very, very far. For example, I use this kind of model, the Russell complex model, that can describe emotions with two coordinates. So it's a epistemological forcing that you can use. These challenges are inside the interdisciplinarity, and if you want to stay in the boundary zone, you have to control them, and you have to be creative also to manage with this kind of obstacles. Thanks a lot. Okay.